Hi, everybody. Welcome to Science Show and Share. We are so excited to have you here and getting started in just a little bit. My name is Daniela Pennycook. I'm joining from CU Boulder, Colorado. And we're going to give everybody just a couple minutes to join our stream this morning before kicking off and talking about atmospheric rivers. Thank you everybody for joining today. All right, I see some folks joining the stream. Thanks for joining us today. Feel free to comment in the YouTube comments and share where you're joining from. We're so excited to have you here. And we're going to start in just 1 minute. I have set up a Slido for today in case anybody would like to answer some questions live with us or share questions in the Q&A. I'm going to share this screen now with everybody so that we can see how to join here. So you can join at slido.com. You can join on your phone. You could join on your computer. It'll prompt you to enter a code here. The code is 2305809. And we'll be able to ask questions in the Q&A. We'll also have some poll questions today. So let's start off with where are you joining from? Feel free to share here where you're joining from. And I'll pull this back up later today throughout the presentation. Awesome. Welcome to our new viewers. We're so excited to have you here. I'm going to put the Slido in the comments so we can keep using this throughout the day. Awesome. We have people from all over. I'd love to see it. Well, we're going to get started. Everybody, my name is Daniela Pennycook. I'm joining you from Boulder, Colorado. We are so excited to have you here joining us live today. Continue to drop where you're coming from in the Slido or in the chat on YouTube. We'll be collecting those questions and taking some time at the end of the webinar to answer those. Today's show is brought to you by the Cooperative Institute for Research in Environmental Sciences, also known as CERES. We include the cooperative in the name because we work in partnership with the National Oceanic Atmospheric Administration, or NOAA. And we have two amazing experts joining us today to share more about their work on atmospheric rivers. So we'll learn more about what atmospherics are, how we monitor them, and how they're impacting the U.S. This winter. Our two experts today are Dr. Mimi Hugues. She's a NOAA research meteorologist in the Hydrology Applications Division, where she studies precipitation. And she worked at CERES for 10 years before joining NOAA. And we have Andy Anderson, who's here. He's a forecaster at the Sierra Avalanche Center in the Lake Tahoe area. So he's joining us from California today. I hope you're just as excited as I am to learn more about atmospheric rivers. And I'm going to pass it off now to Mimi.
Thanks, Daniela. All right, I'm going to put my screen up here. Please let me know if it doesn't look right. All right, so good morning and good afternoon, everyone. As Daniela said, my name is Mimi Hugues. I work at NOAA's Physical Sciences Laboratory, which we call PSL. It's one of the research laboratories that NOAA operates to make its weather forecasts better. And I'm going to tell you, sorry? Okay, I'm going to tell you all what atmospheric rivers are, how we observe them and measure them, and why we care about them. So the laboratory that I work in, one of the things that we spend a lot of time on is trying to learn more about things that make it rain or snow a lot. So this little cartoon here shows you some of the features in the atmosphere that can cause extreme precipitation events in the United States. So a lot of you are probably familiar with or have heard of tropical cyclones. When they get really intense, they can be called hurricanes. I'm not going to spend any time on these, but I just wanted to give you a sense for what sort of class of things atmospheric rivers sit in. So atmospheric rivers are in some ways the West Coast version of tropical cyclones or hurricanes. Mesoscale convective systems are another way that a lot of precipitation forms in the United States. And these are basically big organized complexes of thunderstorms. But in the western United States, the things that basically bring the most rain and snow are extratropical cyclones. These are really big cyclones that form because of the temperature gradient between the cold polar region and the warmer subtropic and tropical regions. And the focus of the talk today, atmospheric rivers. And I'm going to talk a little bit more about both extratropical cyclones and atmospheric rivers, because it turns out that atmospheric rivers often form in conjunction with extratropical cyclones. So extratropical cyclones, often you can sort of see them if you look at a satellite image of the Earth, because they have this really characteristic comma shape in their clouds. So here is an extratropical cyclone that is sort of making landfall on the western United States. You can see California here and Washington and Oregon. And this is the northeastern Pacific Ocean. And this big comma cloud is really characteristic of extratropical cyclones. And these form because basically the cold air moving down from the northern regions and warm air moving from the southern regions sort of get wrapped around each other. And they are associated with cold fronts and warm fronts that you can see on a weather map. And one of the big features of an extratropical cyclone is sort of a warm conveyor belt. This is warm, moist air that is sort of moving up. It gets wrapped up into this cyclone, and it tends to sort of form along the leading edge of the cold front, so just out ahead of the cold front that's forming. And sometimes
Oh, sorry, everybody. It looks like we had a slight connectivity issue. Hopefully, Mimi will be right back in the stream. In the meantime, I'm going to share our Slido, and if anybody has any questions, things they're wondering about atmospheric rivers, now is a great time to share those in the Q&A. So sorry to lose our connection here right in the middle. I'm going to come back to our Slido. And maybe we'll skip over to this question. We'll start here. We'll revisit this at the end of our talk. Have any of you ever seen an avalanche? And if you said yes, maybe drop in the comments or in the chat, where have you seen an avalanche before? Where are you coming from that this is something you've experienced? Yeah, and one example or things that you could include in this is maybe snow sliding off of a steep roof or off of a mountain or a hill. Have you seen snow sliding, large amounts of snow sliding down something steep before that's similar to an avalanche, but maybe not coming from a mountain? Andy is letting me know here we call that a roof-a-lanche. I'm going to give Mimi maybe one more minute to connect back in. And if I don't see her pop back into the stream, then we're going to shift over to our other speaker and we'll circle back with Mimi back towards the end of the stream. If anybody has any questions right now, I would love to hear your questions in the chat. Feel free to comment on the YouTube right there, and we'll be able to see your questions and your answers. We're excited to answer all the questions that you have about atmospheric rivers this year. Okay, I'm going to go ahead and add Andy to our stream. And I'm going to take our poll down here for a little bit. Andy, I think you're still muted. And we're going to go ahead and we're going to jump right into Andy's presentation here. Sorry to switch it up on all of you, but hopefully Mimi will be able to join back in here in just a minute.
Great. Thanks, Daniela. Welcome, everyone. And this is something that is pretty exciting for me to talk about because, as Mimi was going to say, atmospheric rivers, they're really big storms. And I'll talk a little bit about that as well. But one of the things that they do when they hit really big mountains is they tend to contribute to the avalanche danger. I mean, it looks like several of you have seen some avalanches or heard of them or things like that. Avalanches it's basically just snow sliding down a hill, and it can affect anyone who lives in a place where snow accumulates on a steep slope. And that could be your roof. It could be the hill outside your house where you go sledding. It could be the ski area. It could be mountains that you like to recreate in or go snowshoeing or snowmobiling or backcountry skiing or whatever that may be. Avalanches are near and dear to my heart. It's a really fun thing to study and look at and forecast. And I could talk for hours about them. So I will try not to do that, but feel free to ask questions if you have them. So before we get into talking about how atmospheric rivers and avalanches interact and how the atmospheric rivers exacerbate avalanches, I wanted to touch on some very basic ingredients that are needed for an avalanche. And that would be, you need some sort of weak layer in the snowpack. And on top of that weak layer, you need to pile a stronger, more slab-like layer. And all this needs to be sitting on some sort of slope. Once you have that, then you need something to break that weak layer, like a trigger. In this case, it was a skier. That trigger could also be more snow. It could be animals. It could be snowmobilers. It could be grooming machines at a ski area. Anything that adds weight to the snowpack and adds enough weight to break that weak layer below the slab can be a trigger. So atmospheric rivers, they tend to be very large storms. They include massive amounts of precipitation. They often have hurricane force winds. They often have high precipitation intensity. So not only do we get a lot of snow or rain, it happens very fast. So we may get a foot of snow in an hour or something like that. Or 2 inches of snow every hour or 4 inches of snow every hour or something like that. And then they also tend to have variable snow levels, meaning the temperature changes a lot during these storms. So an atmospheric river can give us several of those ingredients needed for an avalanche on its own. Massive amounts of precipitation, we can get feet of new snow. And so that could be a really heavy load on an existing snowpack that could break existing weak layers that were there before the storm. Hurricane force winds, again, we can blow a whole bunch of snow onto a slope and magnify the accumulation that happens by just wind moving snow from one side of a hill to another. Again, that can produce a very heavy load. It can also produce a very slab-like layer where the wind packs the snow together. High precipitation intensity, again, we can add large amounts of snow to a snowpack in a short amount of time. And with variable snow levels, we can create different layers during this storm. So even if we don't have a weak layer before the storm, we could create one during the storm during, say, a cold period of the storm where it's snowing a little less intense and the snow is all light and fluffy and soft. And then the precipitation intensity picks up, the winds pick up, and the snow level goes up. So it gets warmer, so the snow gets more dense, heavier, and easier to compact. So then we have this nice heavy dense layer of warmer snow sitting on top of light fluffy snow, and that all happened during the storm. So there's some ingredients for the avalanche right there. We could create weak layers, slab layers, all within the same storm. The trigger could also come from the storm by just being a massive amount of precipitation and weight added to the snowpack. So two of our three ingredients for avalanches, a layered snowpack with a weak layer and a strong layer, and a trigger, could come from an atmospheric river. Atmospheric rivers don't really reshape terrain, so the third ingredient of steep hillsides, that's already there to start with in the mountains. And these atmospheric rivers, when they come in, like I say, they're really big storms. They have massive amounts of precipitation and snow, and they produce widespread avalanche activity. And a lot of these avalanches are large and destructive, as you see in this picture. There's actually a road at the bottom of this avalanche, and the debris here is 20, 30 feet deep. And that road was closed for, I think, a month this winter, maybe even a little more like 45 days, while they were trying to get all the debris from not only this avalanche, but several other avalanches that hit that road. Now, these things tend to run really long distances. They'll take out mature forests. This is a video of an avalanche that happened during one of our atmospheric river events. You can see this massive debris pile down at the bottom of the slope. And you can see the very distinct line where there are no trees in this gully where the avalanche came down. You can see them all in the debris where it just ripped trees out of the ground, broke them off. And these are strong, healthy trees that, you know, the force of this avalanche was impressive, and it was able to deforest parts of this slope. As you go up the slope, you can see it gouged into the snow, and it'll be interesting to go back here in the spring once the snow melts, well, probably this summer, and see if it did anything to the underlying terrain. In this case, the atmospheric river came in a little bit colder, and we had a lighter, fluffier layer of snow on the ground, and then it got warm, and so it deposited a heavier layer of snow, and it was super windy. And you can see as we get up here to where the avalanche broke, it was the wind blew the snow over the top of the ridge onto these what we would call wind-loaded slopes, and they broke and produced this avalanche. As it went further down, it started training more snow and destroying the forest below it once it picked up speed and funneled into that gully. But these massive avalanches are the hallmark of what happens during an atmospheric river for us. As we get up here to the top of the ridge, you can see where the snow would blow over the top of the ridge and onto the slope below. And it didn't have quite enough speed to take out the trees here at the top, but once it got going, it certainly took out several down here near the bottom. Yeah, so just some more photos of avalanches that have occurred during this winter, during some of our atmospheric rivers. I believe we've certainly had more than 10 atmospheric river events this winter, and probably closer to 14. So you can see how big these are. There's a person standing up there in the top corner, and the debris field below that. And then the photo on the screen with the fireman and the inside of a house is actually the third story of a condo building that got hit by an avalanche this winter. And the avalanche just, invited itself into the house and filled up the condos with snow. Fortunately, no one was injured in that, even though there were people in the building. So these massive avalanche events that accompany atmospheric rivers have some pretty serious consequences. They can impact infrastructure and buildings. They also tend to increase the number of avalanche fatalities that happen, where people get buried by avalanches and then don't survive. This is a slide from a paper from Benjamin Hatchett, looking at how avalanche fatalities and atmospheric rivers are related. And it's got a whole bunch of information on it, but the main pieces I like to focus on are the blue bars in the graph, showing how many of the avalanche fatalities each year can happen during atmospheric river events. That's a pretty significant percentage. And then if you look at the map there, you can see the west coast of the US, Washington, Oregon, California. Those are the places where the brunt of an atmospheric river hits. It hits the west coast, and the most powerful impacts are felt there. And you can see our avalanche fatalities, 2/3 or more in Oregon and California happen during atmospheric river events. And then as you go inland, the storms tend to become less powerful as they pass through several different mountain ranges, and that decreases over time. So that's what I had to say about avalanches and atmospheric rivers for now. And if you all have questions, I'd love to hear them.
Thank you so much, Andy. We really appreciate you being here today and sharing with us what some of the impacts of these atmospheric rivers are having on the ground, and with people who are living and experiencing this in their homes. So yeah, thanks so much for joining us today. Mimi was able to join us again, so we will jump back into her presentation here in a moment. If anybody has any questions they'd like to ask Andy, we would love to hear from you. You can add those into the YouTube chat here just on the right side of your screen, or feel free to share those in the Slido. All right, Mimi, I'm going to bring you back onto the screen here. Thanks, Mimi, for joining us and working through some of your connection troubles. I know, living in this hybrid world, we're all experiencing some of that every day. So we're going to jump right back into your presentation here on atmospheric rivers, what they are, how they happen, and how we monitor them.
Thanks. And I hope you can hear me, and I will keep you over here, so hopefully I don't get disconnected again. Great. So I'm just going to keep the screens up here. It's not in presentation mode, but I think it'll be fine. So I'm going to jump right in, try to go through this. We did this sort of backwards. Now we had impacts first. So you've seen all of the snow that atmospheric rivers can cause. And I wanted to start by just sort of framing atmospheric rivers with other things that make it rain or snow a lot for the United States. So many folks are familiar with tropical cyclones or hurricanes. They are obviously a major precipitation creator for, especially for the sort of southeastern United States. Mesoscale convective systems, these are big complexes of thunderstorms that form and can cause a lot of rain and snow or mostly rain for the central United States. And then extratropical cyclones, which are big sort of swirling masses that form because of the temperature gradient between the cold polar regions and the warm tropics, and atmospheric rivers. And I'm going to spend the rest of the time sort of talking about a little bit more about extratropical cyclones, and then we'll talk more about atmospheric rivers. The reason I'm talking about extratropical cyclones in conjunction with atmospheric rivers is that often they form together. So an extratropical cyclone will actually be the reason that an atmospheric river forms. So this is a satellite visible image that shows sort of clouds that are here off of the coast, the Pacific coast of the Western United States. And if you've ever seen a big comma cloud, this is a feature that is sort of stereotypically associated with an extratropical cyclone. And the reason it forms this sort of comma shape is because, as I said, it's the cold air from the Arctic sort of moves around the one side, and then there's a warm air mass that's moving on the other side. And these two air masses are kind of swirling together. And the warm air mass has a lot of water vapor in it, and will actually can cause basically all these clouds. And you can see the clouds sort of swirl up here. And so this image shows not only an extratropical cyclone, but there's also an atmospheric river here that is impacting the California coast. So this big long line of clouds here is sometimes what an atmospheric river will look like from a visible sort of cloud image. And I've just, to sort of drive that home here, have put the cartoons back from the other slide on here. So you can see here's this extra tropical cyclone. It has a cold front and a warm front, and that warm air mass that is moving out ahead of the cold front is basically what causes the atmospheric river. And here the atmospheric river is this funny rainbow, which is basically a big plume of enhanced water vapor. So here is a movie of water vapor sort of moving around. Again, here is the Western United States. Here's Alaska up here. And this is water vapor. It's like a little movie of how water vapor moves in the atmosphere. So this is if you looked and you took all the water vapor in the atmosphere and sort of condensed it down. The reds, for example, would be about 5 centimeters of water vapor here in the atmosphere above you. And as the waves in the atmosphere, so the extratropical cyclones kind of churn and mix, they can sort of bring up some of these plumes of enhanced water vapor. And that, again, that would be an atmospheric river here, where you get this big elongated plume of water vapor that's moving too. So it's not sort of just sitting there, but it's actually moving toward the Western United States. And these carry tons of water vapor. The amount of water that's in these is 7 to 15 times the amount of water that's exiting the mouth of the Mississippi River. So this is a huge amount of water. As I said, they're often, but not always, part of an extratropical cyclone. They can contribute up to 50% of the annual precipitation in the Western United States. So they're really important for our water resources here in the Western US. I'm in Boulder, Colorado, so really important for our water resources. But they also can range in intensity from beneficial for water resources to flood and mudslide and other impact inducing. And so it's really important that we try to understand them better so we can get at some of these impacts and better predict them. So why do they make so much rain and snow when they make landfall? So again, there are these plumes of warm, moist air that are moving sort of towards, sort of directed fire hose-like toward the terrain of the Western United States. And as they make landfall, they sort of hit the mountains of the Western US, and they are water vapor when they're sort of at low elevations, but the mountains force them to be lifted up. And that causes the water vapor in the atmospheric river to cool. And as it cools, it condenses into clouds and into rain and into snow. And that is the reason, basically, the terrain of the Western US is acting to wring out the moisture in the atmospheric river really effectively. So that's the reason that they make just so much rain and snow when they make landfall in the Western US. So how do we measure them? Well, I have already shown you a couple of the ways. A lot of our knowledge about atmospheric rivers and how and where they form is from satellites. So this is a visible image showing the clouds. Some of the first studies of atmospheric rivers actually used these images of water vapor that are retrieved from microwave imagery on satellites. So this is a little cartoon of a satellite called the SSMIS, and the M in that is for a microwave imager. And that is one of the main ways that we sort of started with our information. The laboratory that I work, the Physical Sciences Laboratory, has also developed some instrumentation that we can put sort of on the ground that will look up and see how much water vapor and winds and other things are in the atmospheric rivers sort of as they pass over our heads. So that's another way that we measure them. And then I wanted to talk briefly about models, because even though this isn't a measurement, it is a way that we get more understanding about atmospheric rivers. So the models that we run, which are sort of in this cartoon, just a big computer, yeah, these models are just, we take the math equations of the atmosphere and we integrate them and solve them with the computers, and sort of can use those to take all the observations that we have and sort of fill in the holes where we don't have observations or for variables that we can't observe, and then produce the weather maps that we have. And we can also use those models, of course, to sort of move forward in time. And we basically are predicting the future with math, which is super cool. So another way that we measure them that I wanted to talk about, so some of you may have heard of NOAA's hurricane hunters. We obviously we fly around hurricanes and we understand them, but we also do this for atmospheric rivers. I was lucky enough a couple years ago to fly on one of these planes. So this is the plane that I flew on. And this is an image from the cockpit at the time from that flight that I took. And these planes have radars in them that can look into the cloud and the rain below and above the airplane. They also have ways that we can actually drop instruments down into the atmosphere. So this little video here shows how we drop dropsondes out of the airplane. So I'm just going to play here. You can see there's a little hatch. We open the little hatch. We drop the little dropsonde down through the hatch. It's really loud. It's very, very loud. The plane itself is loud, but that was even louder when we were experiencing it. And then that dropsonde sort of flies out a chute in the airplane. And once it comes out of the airplane into the atmosphere, it opens up a little parachute and it sort of slowly falls down through the atmosphere. And as it goes, it takes measurements. So these are some of the measurements that that were taken by the dropsondes from the flight that I was on. These are measurements of temperature and dew point temperature, which is a measure of the moisture content of the atmosphere. And then we also got winds from those flights. So I'm almost done. I was going to say, you're going to hear a lot more from Andy. Well, you already heard from Andy about some of the impacts. Another one of the impacts that atmospheric rivers, and this is on the devastating side, is that they can rain so much or snow so much that they overwhelm our water infrastructure. So an example of this was in 2017, there were a lot of atmospheric rivers that sort of landed in California that year, and they caused extreme precipitation and resultant inflows into Lake Oroville, which is California's second largest reservoir. And damage to that reservoir spillway resulted in evacuation of almost 200,000 people. And this was a $1 billion disaster that year. So it was a huge, huge disaster that we had to contend with. And I'm going to go through I'm not going to spend a lot of time here, but I just wanted to point out that one of the things that we study here in my laboratory is not only sort of the current atmospheric rivers and try to understand their phenomena, but we also are looking at how they change with climate change. So I led a study a couple of years ago that looked at how different sort of flavors of atmospheric rivers were changing. And we found that moderate atmospheric rivers in this study looked like they were actually going to be decreased in the future, but extreme atmospheric rivers were increasing. And I will say that this was just for some models. So we're still working to sort of flesh this out a little bit better and understand it more and know if it's actually going to come to pass. But this is work that we're actively doing. So with that, thank you very much.
Thank you so much, Mimi. That is so interesting and also pretty incredible and sad how devastating some of these atmospheric rivers can be. I'm going to bring Andy back onto the stream as well so that we're all together here. And I'm going to take these slides off. Thank you both so much for joining us today. It's really, really interesting to hear more about these atmospheric rivers, what they are, how they're created, and how they're impacting us here in the US. We're going to take some questions here for the next 15 to 20 minutes. So if anybody has questions, please send those here in the chat. We would love to hear from you all and answer some questions that you have about atmospheric rivers. And maybe we'll start with the inspiration for this webinar, which is why are atmospheric rivers so intense this year? We've been hearing about all of the snow in California and in the West, and I've seen some pretty incredible photos of people's homes with these huge snow walls surrounding them. So can you both talk maybe a little bit more about why these are so intense this year? What you're seeing, maybe Andy, what you're seeing out in California.
Sure. I don't have an answer as to why they are so intense this year or why there are so many. I think that Mimi's expertise will serve us well in that question. But I'm very interested to see more about your study as how we're seeing more extreme atmospheric rivers as climate changes. But in terms of the things that have happened for us, at least, for the Sierra Nevada mountains, we've had a record-setting snow year due to the combination of both atmospheric rivers impacting the area, but it's also been a colder winter, and so we've had more snow than rain, and that's resulted in snowpacks that houses are collapsing and roads are closed and washed out, and then now we're starting to look at flooding events from all the snow melting because all that water is now stored in our mountains. So, and we're supposed to have a record-setting high temperatures over the next few days. So we may hit 80 to 90 degrees in Reno near us.
Yeah, and I can't say specifically why this year. I don't know that we've done a careful analysis to say exactly why. I will say it's very unlikely that the reason that we have so many atmospheric rivers this year is due to climate change. Atmospheric rivers are really variable. The number that we get every year depends on a lot of things. It depends on the state of the ocean. In particular, folks have heard of El Nino Southern Oscillation. So that plays a large role in determining how many atmospheric rivers and how much precipitation we get each year. And the reason is because it can basically set up favorable atmospheric conditions that sort of make it easier for the waves that cause the atmospheric rivers to sort of form and sort of propagate down into the right place.
And Mimi, I was reading that we've been in La Nina these past 3 years and we're moving into El Nino next year. Is that correct?
I should have looked.
And so I'm curious when, you mentioned these two phenomena. So in which one would we be maybe more likely to see more atmospheric rivers? Does it work that way?
It's not quite that simple, basically. So I think the short answer is that it, like an El Nino, makes it more likely that you'll get atmospheric rivers in certain portions of the Western United States, and it makes it sort of more favorable, but it doesn't guarantee that you're going to have a lot more atmospheric rivers that year. And in fact, it's a combination of like longer term things and things from the ocean like El Nino, and also other states of the atmosphere like the Madden-Julian oscillation. And also sometimes you can just have, a pattern set up, a wave pattern in the atmosphere that's really favorable. That's not due really to either of those, but just sort of a random chance sort of thing.
And I can expand on that a little bit. We are going into an El Nino pattern coming out of a La Nina pattern, but the atmospheric rivers, their impacts are really felt where they make landfall, and so depending on how far north or south they hit is where you're going to see the most impacts. And so like Mimi was saying, these storms, how many we get in a particular year is hard to predict. And even harder is, which part of the West Coast is going to experience the most impacts from those particular storms. We like to say for our particular region of Lake Tahoe that we can measure a good winter, or we can measure whether or not we have a dry winter or an average winter or a wet winter, basically by the number of atmospheric rivers we get. That's where most of our snowpack comes from. And so, in a drought year, we may only get 2 atmospheric rivers. In an average year, maybe we're looking at 4 to 6 atmospheric rivers. In a record year like this, we're looking at 10 to 14. So, they're a very interesting phenomenon. And I guess I have a question for you, Mimi. I've heard them described as leftover tropical storms from the Pacific Ocean, like Indonesia area, that end up that fall apart, but end up picking up moisture and making their way across the ocean and creating more of an atmospheric river rather than a hurricane. Is that an accurate description?
Well, so they can form from different mechanisms, and we've definitely seen atmospheric rivers that have sort of formed from remnants of tropical cyclones in the East Coast. Usually, I do think for the Western Coast ones, I think of atmospheric rivers as forming, as I mentioned, in conjunction with these big extratropical cyclones. But the connection then to those remnant tropical cyclones is that those can cause basically waves that propagate across. And so there is this connection piece between sort of the Western Pacific and the Eastern Pacific. And yeah, of course, the moisture there just gets sort of cycled and moved and cycled and moved. So, yeah.
I have another follow-up question. I'm wondering, Andy, could you talk maybe a little bit about how you forecast and talk a little bit more about your work in forecasting?
Is that one for me, I guess?
Yeah, that one's for you. We'd love to hear just hear a little bit more about what you do and what's involved in your job, and how do you go about that?
Yes. So avalanche forecasting is a combination of both looking at weather models and remote sensing data and things like that, as well as getting out and looking specifically at what's going on in the snowpack. So in a nutshell, what we do is we go out early, we go out in the field and we dig holes in the snow and we look at what kind of structure there is to the snowpack. Which layers are weak, which layers are strong, what it would take to break the weak layers. And so then that way we have a map of what weak layers exist across our region. And then we try to figure out what we need to do to break them. Is it just to add a skier on top of it? Is it add 6 feet of new snow with an atmospheric river over the next 2 days? Is it nothing and they're just going to break naturally today because they're so unstable? So once we figure out where these weak layers are and how strong they are, what it might take to break them, then we can use that to predict when they're going to break and what you might do to trigger an avalanche. So we take all that data, collect it during the day, and then in the morning when we get up to write an avalanche forecast, we look at that and we're like, okay, well, here we have all these weak layers. They're on these aspects in these particular areas, and overnight we got 2 feet of snow, but that's not quite enough to really cause widespread avalanche activity on these weak layers. But it is enough so that if we add another little bit of weight, like a person on top of that, then they might be able to trigger avalanches. So then we write the avalanche forecast with that in mind, focusing on what kinds of avalanches people might trigger that day, what they might do to trigger them, and where they might be. That's a short answer of what I do.
That's great, Andy. Yeah, I think
an even shorter nutshell is I dig a lot of holes in the snow.
I was going to say, I'm picturing you in a big snow pit right now, checking those layers. Do you release those forecasts every day?
We do publish forecasts every day. So most avalanche centers, there's avalanche centers all across the West, and there's one in New Hampshire as well. And we all publish avalanche forecasts every day during the winter. I suppose we could publish forecasts every day in the summer and we would be really accurate, but people aren't as interested then. So, depending on the time in the Avalanche Center, it depends on what time they publish. We publish ours at 7 a.m. in the morning. Some people publish them at like 5 p.m. the night before, stuff like that.
Awesome. Thanks, Andy. I have a question for Mimi. Sarah Anderson, who's joining us from Michigan, she said Michigans have very mild winters, or this year they had a very mild winter. And her question is in Michigan, is she too far east to feel these effects of the atmospheric rivers that are hitting the Western United States?
The short answer is probably because the water, I didn't talk about that, but the water vapor it does make its way sort of in and across the Western United States. It doesn't only impact California and Washington and Oregon, but there's a lot of mountains between the Pacific Ocean and Michigan. And so my guess is that, most of the atmospheric rivers are pretty wrung out by the time they get there, if they get there at all. The other thing I guess I would say is that the conditions that sort of set up a real favorable it's like a wave train almost for atmospheric rivers to be hitting California also could potentially be unfavorable for extratropical cyclones making their way to Michigan. So there's a chance. I haven't studied that, but there's a chance that there's some sort of mutual exclusivity there.
Thanks so much, Mimi. And another follow-up to that is, would we see, do atmospheric rivers happen all year round, or is this a winter phenomena?
They do happen all year round. They sort of shift where they land. So the storm track kind of moves around with the seasons. So the sort of earlier fall, the atmospheric rivers are sort of more likely to hit sort of in Washington, Oregon, and then later into the winter, then they can hit California. The atmospheric rivers in the summer, they're still there. So if you looked at an image of water vapor, you'd still see the sort of tongues of water vapor indicative of atmospheric rivers, but they're a lot less likely to make landfall. Extratropical cyclones just don't happen as much. So it's just, they're less impactful for the United States, at least in the summertime.
Well, we are coming into the end of our stream here. I'm open to taking any more questions if anybody would like to add another question into the chat. Maybe I'll ask one more. I'm really curious to hear from both of you. What's the most interesting or your favorite part of the work that you do?
Who wants to go first? I can say I really like the it's hard to quantify it, but it's like I actually get to touch a lot of different things. So I get to look at atmospheric rivers and how they change in the future, but I've also been doing a lot of work sort of on the what happens after they make landfall. And I love the diversity of my work. So it's like I get to sort of study a lot of different things, and that's probably my most favorite part of my job, is sort of seeing all the whole chain of things.
I think for me, most people, when they think about what I do for work, they're like, oh, your favorite part of the job must be the commute where you get to ski back and forth from where you go. You get to ski at work. But for me, that is a pretty awesome part of my job. But my favorite part is actually the balance between the physical challenge of collecting the data, like getting out into the mountains in very challenging conditions and digging holes in the snow and figuring out where those weak layers are, balanced with the mental challenge of processing that data and then creating a product that takes a whole bunch of complex science and makes it usable for all of us. So that balance of mental and physical challenge is my favorite part of the job. But like I say, the commute on skis is pretty nice too.
That's awesome. Thanks, Andy. We did get a couple more questions here before we wrap up. So two great questions that came up is when does avalanche risk start to subside in some of these regions?
Well, avalanche risk goes up and down all winter long. And really, if there's enough snow on the ground to play in it, then there's a potential for avalanche risk. So, the type of avalanches you're worried about changes over the course of the winter. As we move into spring, we worry more about wet snow. As the snow melts, it tends to, water flows downhill on any steepness. And so as the snow gets closer to water, it's less likely to stay in place. And then during the winter, we worry more about these dry snow things like wind slab avalanches or avalanches that happen on weak layers that form during the winter. But yeah, so the avalanche risk really is there as long as there's snow on the ground.
Awesome. Thanks, Andy. One more question, and I might have a follow-up here, but how do hydrologists plan to manage all of this snow melt from this extreme atmospheric river year?
That's a really tough question.
That one, maybe?
Well, I am not a hydrologist. I am a meteorologist. And we do work a bit with hydrologists, but I know it's going to be a big challenge. And I think right now they're just sort of trying probably to figure out how much water there is. And then once they have that, they'll figure out what they're going to do with it.
Yes. And likewise, I'm not a hydrologist, but like Mimi, we end up talking to hydrologists because we're all worried about snow and stuff. And I know some of the things that they're doing is trying to figure out creative ways of not only how to predict how much water there's a lot, but also, we've been going through these drought, wet cycles where many years we don't have enough water, and then this year we have too much. And so they're trying to figure out how to store that and be able to use it later in the season. And one of the creative ways that they're looking at is, typically they've not, is managing releases from dams so that we can release a little bit of water now to account for the fact that there's a ton of water sitting in the snowpack that's going to come down into those lakes, and then trying to figure out, where they can hopefully get some groundwater recharge and stuff like that as well. But it's a good question. I'm not sure anyone knows the real answer yet.
Yeah, it's definitely going to be a challenge this winter. We've been talking a lot about all this snowpack and how it acts as this, essentially a reservoir of water that gets stored. So as the snow melts, all this water gets released, and where does it go and when does it get released? And how can we, maximize the use of the water for agriculture and to support the West? Are there any positive impacts? Or can you talk maybe just very briefly on some of the positive impacts that we'll see from this extreme atmospheric river winter?
I mean, I think Andy already mentioned that we're hoping that this will alleviate some of the drought we've been facing, recharge some of the groundwater, and I don't know, Andy, if you want to add anything.
Yeah, I mean, those are two really big positive impacts. Like, we need the water. There's some question about how it'll impact wildfire season as well. There's at least with snow on the ground for extended periods, wildfires are really hard to start when there's several feet of snow on the ground. So in those areas where the snowpack's going to stay into the summer for us, that'll reduce some of the wildfire risk in those areas. But then on the flip side, the amount of water will also allow more vegetation to grow. And some people think that as that dries out later in the summer and fall, then there'll be more fuel for fire as well. So it could impact wildfire in both a negative and positive way. And then, like you said, maybe the groundwater recharge, the reservoir filling. That's, we've moved out of drought status in California for a little bit at least.
Well, this was extremely interesting. It was really nice to hear from both of you on this phenomena that we're experiencing this winter. I know I definitely learned a lot today, and I hope some of our folks who are joining us from all over the U.S. have also learned a couple things. We would love to hear from you. If you have more questions, please reach out. This is how you can get in contact with us. This is our website. We've got our email and our newsletter on there. Please feel free to join us and connect with us there. Mimi and Andy, thanks again for such an informative and interesting webinar. We really appreciate you taking the time to be here today.
Thanks so much.
Thanks for having us.